Today our presenter is from CredC at the University of Houston, and it's Denise Gurkhan. I may have missed the pronunciation, so Denise, maybe you can correct me when you come on. And this talk deals with problems in communications in industrial control systems, and particularly in oil and gas, but also in the electric sector, that have been identified by the LOGIC project, which stands for Linking Oil and Gas Industry to Improve Cybersecurity. I was involved in it in its original incarnation, and also the Department of Homeland Security. And the problem is that these communications take place over lossy, unreliable networks that cannot support a number of things like encryption, and that they must be made secure even though the hardware, the components that have to communicate may be in the field for a long time, many generations of cyber and communication technology evolved over the time that this equipment is in the field. So this presents a number of challenges which the University of Houston and Denise are addressing. And without further introduction, I'll turn it over to Denise.
Thank you. You just pronounced my name perfect. I use it as Denise, although it's Denise, like the boy's name and with a Z, but I mean, Denise is just fine. Thank you. Good afternoon, everybody. When I put the participant list on my screen, is it blocking my slide at all? Do you have any blockage? Do you see any gray on my slide?
Just at the very top, Denise, there are the little boxes that come up when people are talking. But the content itself is clear. Your voice is a little less clear now. I don't know if you have gotten on speaker, if you can get
okay.
Can you tell everybody else to mute?
Is it better?
They're all muted.
Okay.
Right. Speak again.
Is this better? Can you hear me better now?
It's okay. I think it should be okay.
All right. I will try to speak like this. So thanks for the introduction. Indeed, we do use logic documents to justify our case on this project and come up with a clear problem definition. And this talk is about our project on a network function for reliable and secure control messaging over commodity transport networks in oil and gas industry. This is Denise Gurkhan. I'm a professor in the computer science and computer engineering technology program, along with Nicholas Baston, who is a research professor in our lab. And our master's student, Stuart Baxley, is working on the research and development of network function as part of his MS thesis in the network communications track. We have been working on this project for about a year together. And please don't hesitate to contact me over this email if you have further questions after this or any discussion you would like to have. Let's see. There. So today I will talk about our research on developing a network function. I will present an example use case for the industrial control system that may be present in oil and gas industry. I will continue on with the methodology we follow for the network function research to further elaborate on our design, implementation, deployment, and testing. After a summary, I would like to briefly present an overview of our testbed, which allows us to conduct applied research in a realistic network environment, which is key in our research. There we go. So let us first talk about what we mean by a network function. Development of a network function involves the thought process of how logical functions may be applied to specific flows in the network. These logical functions may be filtering on particular match packets, tracking of particular features in the packet. You might be detecting signatures, or possibly even redirecting flows in the network. For example, given a network topology that I'm showing here, with servers located here on the bottom right, and many scattered users over the network. We may have network functions deployed on any of these vertices of the topology graph. And these network functions may be applied to flows defined by particular header fields in the packet streams in the network. The network function in turn would match such header fields to identify the flow it would be applying the logical operations on. So here's the example view that we are using for the oil and gas industry's industrial control system. Potentially, there are serial and other minimum overhead protocols being used to carry sensor and control signals through this network. And we are assuming there's a central management and monitoring site that may be connected with the remote sites A, B, and C, or more to oversee these operations. In this respect, it is essential for the central site to receive information from the remote sites whenever there's any available. And we assume the connectivity is through the internet with low-speed commodity transport. And we also assume that the device communication is composed of some sensor readings and control signaling. So our project is based on such a scenario in broad strokes. So we assume an existing hardware and network technology present for the industrial control system that will facilitate this data exchange between sites. And we would like to deploy our network function without replacing this existing equipment. Furthermore, we envision a logical functionality that will enable like single point of testing and configuration, and it should support the natural evolution of needs, let's say, in this industrial control system. And we assume these needs are going to be based on considerations on security and safety as the system gets more complex. As a separate item, since these individual devices have specific hardware requirements based on the environment that they're operating in, a network function deployment should also be decoupled from these system device capabilities and their specific hardware refresh cycles, because they are very different compared with networking technology evolution from a systems perspective. And if we look at logical operation of network functions, we would like to also address the networking issues to provide resiliency. In that respect, messages should be delivered in order of their posting, and we should be able to handle the ordering of messages per site, device, and flow when needed. Also, we have a requirement to secure this information flow through encryption on these network functions. And we would like to realize all of this operation, all of this functionality in a transparent manner so that the end systems will not have to change their current operational state. So now that we have a driving use case, I will move on to describing the methodology of network function research with these following steps that I'm showing here. So we have agreed on a problem definition with our collaborators, and based on reports on oil and gas industrial control systems, cybersecurity vulnerabilities, the deployment constraints and solution requirements feed into this process at this early stage so that they will scope our research. And we work on the logical function design. This step involves extensive research on how flows should be handled at the network functions while also defining system-wide policies. In that respect, our design cycle builds the security considerations into the process. We then move on to validation, implementation, and testing on the network science and engineering research testbed, which I'm going to present in a little bit. So our problem definition is derived from the main cybersecurity issues we target in oil and gas industrial control systems. The fact that all control system data exchange is happening over the commodity transport poses security challenges as well as operational shortcomings. We have scoped the work to solve this problem with particular guarantees to deliver in order and lossless packet streams from sensors at sites in a secure manner. We are constrained by the existing deployments of industrial control systems. In that respect, we cannot really suggest a complete overhaul, and we would like to not change the existing infrastructure. So we would like to decouple basically the resilient solution from the existing hardware in the ICS. Our constraints basically are we would like to be as vendor independent as possible because the vendor solutions vary according to the feature set desired in each environment. We would like to be state sensitive to the limited compute resources in these environments, and there should be no impact on the existing balances. And let me switch gears to show you some of our progress in realizing the logical function design of the network function. The slide is pretty easy. I'm actually showing about a third of the flow chart for handling lossy packet streams for the flows of interest, let's say from a site in our scenario diagram that I showed earlier. It starts with a packet received, and then it follows through with actions and decision points in our network function. And this flow chart is in some pseudocode language so that it can move on to implementation in a smooth manner or move back up to policy definition, the governing policy of this design with relevant parameters that we want to tweak. So let me zoom in to provide more detail. So for example, a packet will be processed through different logical flows based on what incoming port it has arrived at this network function. If, let's say, this is a local packet at a site, we may need to keep a copy of the packet, of the full packet for future in case of handling loss. Or it may have arrived from a remote site. In that case, we need to keep track of packet sequence numbers to identify if there will be any lost packets in this particular flow stream. You can see some decision boxes with checks on policy in this diagram, and we have they will have some pre-assigned policy. So we keep track of policy elements at this stage so that we can guarantee an expected behavior throughout the logical operation, and then we can provide this behavior to the overall, let's say, industrial control system in place and derive an expected reliability measure in return. So another example of the same chart I'm showing top right, where we store a packet in preparation for handling a potential loss, let's say, during its transport. And all of these decisions are tied to the policy of our choice, basically, with the parameters that we want to tweak. So let me describe a little bit of the role of the policy design at this stage. Policy parameters basically indicate a high-level reliability definition and requirements imposed on the system by the overall operation of the industrial control system. For example, an expected state machine is drafted let's say, for requests for retransmissions within this loss handling policy. Let me show that in this next slide. So we keep track of the state of missing packets while also considering the overhead we have imposed on the operation of our network function. For example, a packet missing in the flow stream will start a wait timer in our state machine, and requests for retransmission packets will be sent throughout this timeout period while the system is waiting to resolve this issue. The timeout parameter in this state machine is a function of the policy for how aggressive our system design should be in handling this request for retransmission. This kind of consideration will need insight from resources, let's say, dedicated to provide this level of reliability, and we expect that they will most definitely have a trade-off in system design decisions between resource consumption and the desired level of reliability or resiliency of the contract. So such trade-off is built into our design process so that we can guarantee a measurable reliability promise when the business decisions are being made. In fact, we will keep such parameters configurable so that evolving business requirements may choose to allocate more or less resources based on the reliability level that's desired in the organization. So next, we validate our approach. So I'm showing an example diagram of how we basically go through every possible case of, every possible scenario of, let's say, handling the lossless policy. We go through these cases with the state machines and the process flows, and then we try to see how we're expecting to recover from a lost packet and how we expect to receive the transmission of the lost packet, let's say. Since these flowcharts basically cover all cases, we have a documented reliability guarantee based on whatever parameters we pick for retransmissions and resource allocation. Similarly, we have mapped out how to keep track of ordering of packets, and now we expect to order packets that are lost, let's say, within the packet flow stream. So there's again a trade-off in ordering of packets when multiple sequence numbers may be skipped before an in-order packet arrives at an endpoint. So the maximum number of packets that may be out of order in that range is the resource stretch in the system while keeping track of the state. So this kind of reliability consideration will drive the implementation, but we would like to keep the logical function of actual order of packets preserved in the design and make all of the decisions on the resources at the implementation stage tied to system resources. So let me elaborate on our thought processes for, let's say, providing guarantees for lossless and in-order delivery. So when we are designing, when we are developing the network functions, we are thinking, okay, if we want to guarantee a lossless transmission, then we need storage resources, and these storage resources will store a number of packets in case a site says, hey, I lost these packets, I need a retransmission. And then we need to keep track of bringing up these resources when they are full and they have served the purpose. And we need to keep track of retransmission functions in the network function while keeping each of these parameters dynamic, meaning the number of packets to store, or when to free up, or how long should we wait for retransmissions to happen. These all should be dynamic parameters, and that's what we mean by the programmability of the network function. And all of these parameters should be defined by the policy that is driven by business needs, and basically give a reliability measure back to the business needs of the organization. Similarly, for an in-order delivery, we would like to keep track of the sequence number field in the packet headers and ensure in-order delivery with this storage system helping us with the retransmission. Next, coming back to where we are on our project progress, we are using our network research testbed to test and validate the operation of the network function. We're able to create emulated topologies that are representative of the scenarios provided to us by the ICS expert collaborators we have here, Dr. Art Conklin and Dr. Chris Blank for oil and gas systems. And in turn, we use our research testbed to test our approach. Our research testbed is composed of programmable network function surfaces where we deploy our network functions on the vertices of network graphs. We have an extensive control and management over these vertices through our network orchestration software. We're also able to add various impairments on the edges of our graph for a comprehensive set of relevant validation and testing scenarios. Our testbed provides applied research tools with realistic behavior observations in a real network environment. We also utilize our testbed for the instruction of computer networking to give an observation-based, to actually teach networking in an observation-based manner. So just in summary, we're basically in the stage of finalizing our logical function flows for our network function solution, and we will utilize our testbed for the validation. So at this time, I would like to just briefly present our testbed leading up to the next stage of our project. This is basically a network science and engineering research testbed in the SDM lab at UFH. We have a multi-vendor switch set totaling our capacity to over 1,000 ports ranging at 1 gigabit per second and 10 gigabit per second. And we have various SDN switches in our testbed. We utilize specialized forwarding devices that are emerging in their technology to handle hybrid server switch architectures to handle these network function deployments. And we have CPU, RAM, and storage capacity to run our specialized network graphs on a comprehensive set of advanced topology options for our experiments. Our orchestration software supports multi-vendor networks, and it is equipped with data analysis tools. We also have developed an experiment harness for creation of repeatable and verifiable research data. So just to give a basically sense of what our capabilities are, the orchestration system actually serves multiple purposes. For example, a manual configuration management of devices is common when there is a multi-vendor network present in an organization like this one that I'm showing here. Therefore, there is very small room for accommodating evolving needs of the organization in a dynamic manner, like without having error-prone processes like in config and management, because the system gets more and more complex. Because of this, there is interest in the promise of a centralized control and management in the industry. In that sense, our orchestration system basically can manage and provide programmable configuration hooks for network graphs. So I'm showing actually the network graph, corresponding network graph to the enterprise network that I showed here, the way it would look in our testbed. We can instantiate all those components in a graph and manage them because all of these processes are network functions, basically, that we can program and configure according to our experimental needs. In addition, we can add impairments on the edges of this graph so that we can set up many different experimental options for our applied research in networking. Well, either I sped through the presentation, but I am done. Thank you for your attention. Are there any questions?
Hi, Denise. I was wondering, it seems that many of the features that you're talking about here, for example, of ensuring delivery or maybe reassembly and ensuring that things arrive in order, that is done by the TCP/IP stack. So where can you position your network function insertion with respect to the TCP/IP stack?
Actually, the TCP/IP stack seems like not an option to use all these devices. Obviously, yeah, TCP/IP has been around and it does handle reliable transmission, and it was created for that purpose. But these devices don't have the compute capacity to actually handle the stack. That is the input constraint that was given for the oil and gas systems in place.
Hi, this is Professor. Following up on what Al asked, while it's clear that the TCP/IP could not be implemented in the end devices, it's unclear to me why it or something like TLS or SSH wouldn't be the essential core of your network function itself, rather than re-implementing all that functionality for multiplexing, reliable in-order delivery, cybersecurity, etc. Can you comment on that?
Yes, we were. So we were using the scenario that I presented at the beginning with devices that mostly have serial and very low overhead protocols that they use to push their sensor output into the network. So those devices don't have the TCP/IP stack.
I understand that, but why aren't something like TCP/IP, TLS, or SSH the core functionality of your network functionality box, rather than re-implementing all of that functionality on your own?
Oh, then I would have to define a device with the TCP/IP stack. So, like, I would have to have a TCP/IP stack per device in my network function, which will not be possible. I mean, I see your point, and we have a continuing discussion on this too. It is a resource constraint, though.
Okay. I guess we can talk later.
All right.
Yeah, sure. Yeah.
Any questions locally? Any questions elsewhere in the online community?